Hi everyone, welcome to the first lecture of Macm 201. In this lecture we're going to introduce the fundamental combinatorial objects that we'll be using throughout the course of the term. In discrete mathematics we are interested in finite sets of objects put together with some sort of structure. And that together makes a combinatorial object. So for example, the combinatorial objects we'll be interested in are sets and subsets, strings and permutations, graphs, and a particular kind of graph, which is called a tree. So let's dive into each of these kinds of combinatorial objects today. So sets and subsets. Let's just suppose we've got a set S and it consists of 4 elements, A, B, C, and D. We could ask, for example, how many ways could we choose 3 of the 4 elements from this set? And I'll phrase this as, how many 3-element subsets are there of S? Well, you may remember from Macm 101 that this is the number of ways to choose 3 of the 4 objects, and so the binomial coefficient captures that precisely. It would be 4 choose 3. And you may say, well, I also know that 4 choose 3 is equal to 4 choose 1. But this, in this context, is really saying, okay, I want to choose 3 elements from the set of size 4. That's equivalent to choosing 1 element, which I don't want to keep. So I'll keep the remaining 3. I'll choose the one that I want to throw away. So that means this is equal to 4 choose 1. And how many ways are there to choose 1 object from 4 objects? There are precisely 4 ways to do that, so we can get our answer of 4. There are 4 3-element subsets of S. If we want to enumerate them or write them down, we can use this last idea that choosing 3 to keep is the same as choosing 1 to, let's say, delete, to get rid of. And so if I want to list them out, I'm going to say, well, I'll delete A. That means I will only keep B, C, and D. So there's 1 3-element subset. Or I could get rid of B. I'll delete B, and that means I'm keeping A, C, and D. Or I could delete C, in which case I'm keeping A, B, and D. Or I could delete D and keep only A, B, and C. So we not only counted how many ways there were to select a 3-element subset, we got 4 of them, we also had a way to list them out. And the way we listed them out was we just listed them out by the easier method of figuring out which one we don't want to keep in this context. How about our next combinatorial object, strings? Well, strings consist first of an alphabet, which we'll denote by capital sigma, and that's a set of elements which will be used as the characters of our string, or the letters for the words that we will be making. A string, often referred to as a word as well, so maybe I'll write that down here. This is often referred to as a word of size n, often referred to as the length, is an ordered sequence of n letters from sigma. So as our first example, we'll look at strings over this 2-character alphabet. These 2 characters are often referred to as bits, and so some examples of strings could be 0, 1, 1, 0, 1. There's a 5-character string, or a size 5 string, or a length 5 string. So maybe we'll jot that down here, that this has a length of 5. Maybe we'll do a string of length, let's say 7. So maybe our string could be 1, 1, 1, 0, 1, 0, 1. There's a string of length 7. These strings here are referred to as binary strings. And we've already seen in our warm-up exercise from the previous lecture that binary strings came into play in what may have looked at first glance like a counting problem that had nothing to do with binary strings, but we converted it to one where the thing we wanted to count was equivalent to counting the number of binary strings. So this forms one of our fundamental combinatorial objects, and it's going to come up again and again and again, these ideas of binary strings. Here's another alphabet, A, C, G, T. In this case, strings over this alphabet. Well, for those of you with some biology in your background, you may encounter strings in A, C, G, and T when you're doing DNA sequencing. So strings in these 4 characters are often used to represent DNA sequences. And so, for example, some really short DNA sequences like ACCT or TCCA, for example. There's a couple of strings. One is just the other one in reverse. These are pretty short because, by way of contrast, the human DNA sequence consists of about 3 billion characters. So the length is about 3 billion. So we leave as an exercise at the bottom of the screen to count the number of DNA sequences there are of length n. So there's a natural counting problem associated with DNA sequences. And you may think to yourself that, well, it's a string of length n. Each entry in that string could be one of 4 characters, so it should be 4 to the n. But the problem is it's not, because, for example, this string of length 4 as a DNA sequence is equal to TCCA. So the sequence can be read forwards or backwards. It's still the same DNA sequence. So we would have to make sure we count those 2 sequences as the same. But then a natural conclusion might be, well, I just take that 4 to the n and I divide it by 2, because for every sequence I will get it both forward and in reverse. But that's not true either, because, for example, the sequence which just consists, for example, AAAA, that wouldn't have been counted twice. That would only have been counted once, just the sequence of 4 A's. So there's a little bit of subtlety in this exercise, and I leave it for you to ponder. So let's look at the next example. Find all strings of length 6 over 0 and 1 that don't have 1, 0 as a substring. So we're looking for all the binary strings of length 6 that don't contain a 1, 0. So at any point when we bring up an example like this, I do encourage you to pause the video and try to work through it yourself first. If you don't solve it, that's not a problem. But what you're doing is you're giving yourself the opportunity to internalize the problem, to think about the various aspects of the problem before I present them to you. So this will allow you to learn the material that much better. So what we're going to do is we're just trying to make some observations that are going to help us count. So the first observation is, if we can't have 1, 0 appearing, then it means that a 0 cannot appear to the right of a 1. Okay, that might seem like a very simple statement to make based on the fact that we can't have a 1, 0, but this means actually a lot more. It means that I can never have any zeros appearing to the right of any 1s. So in my sequence, all the zeros have to be clumped up at the start, and all the 1s have to be at the end. And that is going to allow me to count these things. So a 0 cannot appear to the right of a 1, so a string must have the form it's going to be a bunch of zeros that are at the start, and then a bunch of 1s that follow. And since our string is of length 6, what this means is that there are 6 places for the 1s to start. If it's going to contain a 1, it can either start in, the 1s could either start in position 1, 2, 3, 4, 5, or 6. So there's 6 places for the 1s to start, or they don't appear at all. It's just a sequence of zeros. And so that means, therefore, there are 7 strings. So we got our answer. The ones, once we know where a 1 appears, they've got to all be 1s to the right of it, and then zeros to the left of it. So either the 1 can start in position 1, 2, 3, 4, 5, or 6, and the 1s are always going to be to the right of that first one, or the 1s didn't appear at all, in which case it's a sequence of zeros. So let's write them out. They're going to be, you don't have a 1 appearing at all, so 4, 5, 6. That means, essentially, if we want to think about it this way, the first occurrence of a 1 would have appeared in the 7th spot. There is no 7th spot, but we're thinking of it like that. Or the first occurrence of the 1 appears here in the 6th spot, in which case it's all zeros before. Or the first occurrence of a 1 appears in the 5th spot, in which case there's 1s after it and zeros before it. Or it appears in the 4th spot. Or it appears in the 3rd spot. Or it appears in the 2nd spot, or it appears in the 1st spot. And there we go. There's our 7 strings. And so we got them by first making this observation that if you can't have 1 0 appearing, then all the 1s have to always appear to the right of the zeros. This leads us to permutations. So a permutation P over an alphabet sigma is a string over sigma where every letter occurs exactly once. So for example, let's find all the permutations of the alphabet sigma consisting of 1, 2, and 3. So it's going to be 1, 2, and 3, 1, 3, and 2, 2, 1, 3, 2, 3, 1. And if you're thinking, what's my thought process for listing these out? I'm actually just listing them out as words in 1, 2, and 3, and I'm listing them out as they would appear in a dictionary, sort of like alphabetical ordering. So here I've got the smallest character, which is the 1, appearing first, and then the next smallest second, and then the next smallest, which is the 3 third. But then in the dictionary, what would follow 1, 2, 3 would be a 1, 3, 2, with those last 2 characters switched. And then the remaining two words or permutations are, we have the 3 first, and then the 1, 2 appear in order, or they appear in reverse order. And so there's all the permutations we have. How do we know we got them all? It'd be nice to know how many permutations there are in advance. And we can think about that. We just did a set of size 3. Now we'd like to know for a general set of size n. So I can think of these as sort of slots that I'm going to fill in. There's my first position, my second position, my third position, and so on, all the way up to the nth position. Now I think about filling those slots. There are n choices of a character from the alphabet to put there. Once I've placed a character there, there are n-1 choices for a character to go there. And then there are n-2 choices for this character, all the way down to there's 2 choices here, and then finally there's 1 choice for the last one. And so the number of ways I can fill those slots using n letters, where I'm distributing all n letters across here. I'm not using any one more than once, and I'm not leaving anyone out. That means we have n times n-1 dot 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 times 2 times 1, which is denoted by n factorial permutations. We've done it in general. In the case when n was equal to 3, we should get 3 times 2 times 1, or 6 permutations, and we have them. We have 6 permutations. So this is another example of when knowing how to count something without listing helps when you list them. I knew in advance. Now, well, I did the calculation afterwards, but now if I have a collection of 3 objects, I know that there will be 3 factorial, or 6 permutations of those objects. So if I've listed out 6 permutations, I know I've got them all. Now permutations, We're going to see them come up over the course of the term, but I just want to show you a fun little example of where a permutation could be used. Permutations do get used in this context, and this is in cryptography. So for example, I've got a message here. The sparrow has left the nest. Heading, and there's the coordinates of where it's heading, and then passcode. So there's a secret message. And what I'm going to do with this secret message is I'm going to do a permutation on it as a string, just rearrange the characters, and there's the encrypted message. Now you can send that encrypted message off to your spy friends and they can decrypt it and everything's all good. We've sent a message off that will be difficult to crack. So let's just say, for example, that Bob receives the following encrypted text from Alice. So I've got this text mysterybook.txt file, and what I'm going to do is I'm going to read it in and I'm going to do a permutation on the text as one long string. And so there it is. There's our text, one long string. That's just now a permutation. So I permuted all the characters of this book around, and it's pretty much impossible to figure out what it says. So maybe I'll ask you, what book do you think this is? What book do you think this is? Well, Bob knows how to find it because Bob and Alice have worked out in advance what permutation got applied, so Bob can always undo the permutation. And when Bob undoes the permutation, what he gets is I am Sam, Sam I am, that Sam I am, that Sam I am. I do not like that Sam I am. So this is our Dr. Seuss book, Green Eggs and Ham. So just a fun little application of where permutations could get used. There are more serious applications around cryptography where they do get used, but that was just sort of a fun one. All right, what do we have next on our list of combinatorial objects? So in this first lecture, we're just introducing graphs as a combinatorial object, something that we're going to be counting with throughout the semester. It's not till later on in the course that we actually get into graph theory. So graph theory is more about being able to prove things about the structure of graphs. For right now, we are just interested in graphs as an object, something that we can use to count with. So our definition is a simple graph is a pair V and E, where V is a set and E is a set. V is called the set of vertices, and E is a set of edges. And the elements of E are just ordered pairs of vertices. So a typical element of our set capital E would look something like this. We'll call it little e. That's a typical element. It's a pair ij, where I is a vertex, j is a vertex, and if that is an element of the edge set, then we say I and j are adjacent. The degree of a vertex in the set V is the number of vertices that are adjacent to vertex I. So here's a graph. Now if you've been a little bit familiar with graph theory before, you're probably thinking, that's not how I usually visualize graphs. And it's not, but this is from the definition. A graph consists of two sets. It's a set V of vertices, which I've listed there, and a set E of edges. So graphs are often given by diagrams. So for example, this graph here, I'll write out the vertices, 1, 2, 3, 4, 5. Maybe we'll put 6 right in the middle. And so we've got edge 1, 2, edge 1, 5, edge 2, 3, edge 2, 5, edge 3, 4, edge 4, 5, and edge 4, 6. So there's a diagram that represents the graph. Now the graph is what's given in the example by those two sets. This is just one of many diagrams for the graph. So we want to be careful here and not to say that this diagram here is the graph. This is a diagram of the underlying graph. So the underlying graph consists of the vertices, and then the list of connections between those vertices. And that's given in the diagram. So from the diagram, we can write out the two sets, V and E. In other words, we can extract from a diagram the graph. But I just want to be subtle here and say that we don't really refer to the diagram as the graph itself. And the reason is because we could draw another diagram. So here we've got 1, 2, 3, and then we'll maybe do 4 down here, and we'll go 5, and then maybe 6 down here. So there's our vertices laid out, and we've got, again, 1 connects to 2, 1 connects to 5, 2 connects to 3, 2 connects to 5, 3 to 4, 4 to 5, and 4 to 6. So there's another diagram of the same graph. So these are two diagrams of the same graph. Now in the definition we've talked about degree, so we can follow up with that. Vertex, let's say vertex 2 has degree. And what is the degree of vertex 2? Well, in the definition, the degree of a vertex is the number of vertices adjacent to vertex, in this case vertex 2. So if I look at vertex 2, a vertex is adjacent to it if there's an edge connecting those two vertices. So 2 is adjacent to 5, 1, and 3. So there are 3 vertices adjacent to it, so it has degree 3. What about vertex, let's say vertex 3? This has degree, it's adjacent to vertex 2 and 4, so it has degree 2. And lastly, you may notice there's this word simple up here. What's this word simple trying to capture? Simple is really just trying to capture the idea that there's no loops. So a loop would be, if we've got a vertex, a loop would be an edge that starts and ends at the same vertex. So in this case, we are interested in simple graphs. That means graphs with no loops. So that's what we mean by simple. How many edges can a graph with n vertices have? So here we've introduced a combinatorial object graph, and now we're asking questions about counting things related to that object. How many edges can a graph with n vertices have? So if we had one vertex, because we aren't allowing loops, there are 0 edges. How about if we had 2 vertices? How many edges can we have? So we're thinking about what's the most number of edges we can have. With 2 vertices, maybe I'll write that up here, n equals 1. Now in this case, with 2 vertices, n equals 2, we can have 1 edge. How about if n equals 3? Just get a feel for how the number of edges behaves relative to the number of vertices. Well, if n is equal to 3, we can connect up those two, or those two, or those two. So we also get, in this case, we get 3 edges. How about if n equals 4? So there's our 4 vertices. We could have 1 edge, 2 edge, 3 edge, 4 edges. But I can also connect these diagonal ones with an edge. That's 5 edges. And I can connect these ones by an edge. That's 6 edges. What about in general? What if I had vertex 1, vertex 2, vertex 3, vertex 4, all the way around to vertex n? And I want to know how many edges can I have in total? Let's get a feel for maybe how to count these. Vertex 1, it can connect to 2, 3, 4, all the way around to n. So vertex 1 could be a part of n minus 1 edges. It would join up with vertices 2 through n, so n minus 1 edges. So there's n minus 1 edges that we get from vertex 1. How about vertex 2? Well, I don't want to count the one I've already counted that connects it back to 1, so I'll only move forward. vertex 2 could connect to 3, 4, and all the way around to n. So we could connect to n minus 2 other vertices. So there's n minus 2 edges there. Vertex 3, if we just connect it moving forward, it's going to connect to n minus 3, or it can connect to at most n minus 3 more vertices. And we can keep going until eventually we get to vertex n, which we've already exhausted all of the edges it can connect to, so the one before it would have connected to, maybe I'll write that one in here. We got an n minus 1, it can connect to n, and then there was all those ones that went before it. So we have that the number of edges is n minus 1 plus n minus 2 plus n minus 3 all the way down to 1. So what is that? That's the sum as I goes from 1 to n minus 1 of I, if we want to use sigma notation for this. But what is this sum? Well, this sum is given by n minus 1 times n all over 2. You may say, well, how did I get that? There's a nice technique for finding the sum. So we write out 1 plus 2 plus 3 plus dot 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 all the way up to n minus 1. And then we write out that same sum in reverse, n minus 1 plus n minus 2 plus n minus 3 plus dot 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 plus 1. And then we add them all up. I've effectively doubled the sum that I'm trying to determine, but I've done it in such a way that I can work out the value much more efficiently, because when I add up all these numbers on the board, I can see I can group them in pairs, and I get n plus n, so I'm adding these things up, it's equal to n plus n plus n plus dot 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 plus n. And how many are there? There are n minus 1 of them. So this is n minus 1 times n. But that's effectively double the sum that I'm trying to find, so it's n times n minus 1 over 2. So that was just an aside. You may have seen this already if you did calculus 2, for example. But the idea is that the sum of these consecutive integers up to n minus 1 is n minus 1 times n over 2. This is also the same as n choose 2. So how many edges are there in a graph with n vertices? There are n minus 1 times n over 2, but when we write it as n choose 2, that might conjure up another way for you to think of, oh, I can see how I could figure out how many edges there are. An edge consists of a pair of vertices, so it's just a number of ways I can choose 2 vertices from a set of size n, and that's n choose 2. That's another way to think about it, but we did it as a sum in this case. So the next definitions involve definitions of complete graphs, paths, and cycle graphs. So a complete graph, a graph G with vertex set V and edge set E, is complete if it has at least one vertex, and for all pairs of vertices, the edge between those 2 vertices is in the graph. So a complete graph is a graph that contains all possible edges. A path graph, so a graph V comma E is a path if it has at least one vertex, and you can order all the vertices in such a way, so V1, V2, V3, all the way up to Vn, in such a way that the edges are able to be enumerated as V1 to V2, V2 to V3, and all the way up to Vn minus 1 to Vn. So there's some examples of some paths. So there's a path of size 0, just consisting of vertex V1, a path of size 1, which is the 2 vertex graph with an edge between them, and then one of size 2. In this case, size is referring to the number of edges. So size here is the number of edges. A cycle graph is pretty much a path graph with one extra edge that connects the start to the finish. And in this case, we're going to assume that a cycle has at least 3 vertices. So when I look at that last path example of size 2, then we make it a cycle by just joining the last vertex back to the first. So I'll get rid of that because I don't want it in the path example, but that's all it is. And so a cycle graph is one in which the vertices can be ordered in such a way that the edges go v1, v2, v2, v3, all the way up to, well, if I stop here, that's a path, and then we got the one extra vertex on the end that makes it a cycle. So let's bring all of these definitions into these next couple of examples. So we want to find a path of size 4 in K5. So what is K5? K5 is the complete graph on 5 vertices. That was introduced right up here. We denote the complete graph on n vertices by Kn. So K sub 5 is the complete graph on 5 vertices. It means that we've got 5 vertices, 1, 2, 3, 4, 5, and every edge is in our graph. So every edge is going to be in here. And so there we go. Because each vertex can have at most 4 neighboring vertices, 4 vertices that are adjacent to it, it means that every vertex is going to have degree 4, and so I've got to connect it to every other vertex by an edge, and so there's our complete graph. Now we want to find a path of size 4. So for example, a path of size 4 could be something like 2 to 4, 4 to 5, 5 to 3, 3 to 1. So we went 2, 4, 5, 3, 1. And that's a path of size or length 4. How about a cycle of length or size 5 in K5? So again, we'll write out K5 again. 1, 2, 3, 4, 5. We'll throw in all the edges. And now we're interested in a cycle of length 5. Well, a cycle, we could go 2, 5, 3, 1, and back to 2. So 2, 4, 5, 3, 1, 2. And that's a cycle of length 5. If we were to just write it out what it was, I'm going to redraw it, a different diagram for the same cycle. It went 2, 4, 5, 3, 1, and then back to 2 again. So there is our redrawn version, and now it looks like a cycle. It's just goes around the vertices and come back to where it started. Whereas in this example, we had 2 goes to 4, goes to 5, goes to 3, goes to 1. So there's another diagram for that path. A few more bits of terminology. A graph is called connected if there is a path from vertex I to vertex j for all pairs of vertices I and j that are different from each other. So what this means is we can get from any vertex to any other vertex. So for example, maybe we'll just draw a couple of here. So here's a graph. Consists of 5 vertices and 4 edges, and this is not connected. Why is it not connected? Well, if I start at, let's say, call this vertex 1, and I call this vertex 3, there's no way to get from 1 to 3 by imagining these things as sort of the edges as roads and the vertices as sort of destinations. I can't go from 1 to 3. There's no road that takes me, or no series of roads that allow me to go from 1 to 3. And our last combinatorial object that we'll be interested in is that of a tree. And a tree is just a special kind of graph. It's a graph that is connected and it has no cycles. So a tree is connected with no cycles. So just to get familiar with trees, we've got a question here that asks us to draw all unlabeled trees with 4 vertices. So we've got 4 vertices. So there's 1 vertex. I want to draw 3 more and then add some edges. So if I just maybe imagine doing this, I put another vertex down, maybe I'll put another one here, and maybe another one there. So there's my 4 vertices. It's unlabeled, meaning I'm not going to put labels on my vertices. I'm just interested in more of the shape a tree can have, not so much the finer details about whether vertex 1 connected to 2 in this graph or not. So I've got my 4 vertices. I can throw some edges in. I can't connect this one over to this one because that would be a cycle, and a tree has no cycles. So I'm not able to introduce that edge. It's supposed to be connected, so I need to still connect that 4th vertex back to the original 3. I could do that in a few different ways, but maybe as a first step I'll just connect it like this. And so there's one example of a tree. So we'll call this our first example, and maybe we'll make a note that the max degree of a vertex is 2. So that's the maximum degree of a vertex. There's 2 of them have degree 2 and 2 vertices that have degree 1. So there's one example of a tree on 4 vertices. Maybe I'll try to do another one. I'll start with that same underlying structure of 3 vertices with the 2 edges like that. Now I've got another vertex I want to add into the mix. I've already connected, I've looked at the example where I connected that vertex on the end there, so I won't look at that one because I've already counted it. Maybe I'll add this one in red. Maybe I should say, well, why don't I connect it to that one? Well, because it's unlabeled, these 2 diagrams are exactly the same. So that's the same tree drawn. I didn't label the vertices. I didn't put a 1, 2, 3, 4 here, and then a 1, 2, 3, 4 here, in which case I'd say, well, they're different because one connects to 4 but in one diagram but not the other. I'm not interested in that, so I'm not going to label the vertices at all. We just want the underlying structure. So in that context, I wouldn't draw that one because it's the same tree, the same unlabeled tree. So where could I add this new vertex? Well, maybe I'll put it up here. And now I need to connect it with an edge back to the original or the path structure on those 3 vertices. I won't connect it to the either end because it'll give me back tree 1, so I'll connect it to the middle one. And that gives me a new tree, tree 2. And here I've got the max degree is 3. So there's a vertex there of degree 3. And if I think about it, there's really no other way to get a tree where I've got one vertex of degree 3. Because if I start drawing that, a vertex degree 3, then those are my remaining 3 vertices. So any tree on 4 vertices that has a vertex of degree 3 has to be tree T2 that I drew there. Okay, so I'm starting to get the ability to write down or enumerate these trees, or list them out, by maybe fixating on some aspect and going through them. So before, when I wrote down strings, I wrote them down in alphabetical order. Here I'm trying to list out trees. I'm trying to list them out in their order of complexity, if you will, in terms of their maximum degree. So maximum degree 2, here's the one of maximum degree 3. I won't be able to have one of maximum degree 4 because if I had a tree with a degree 4 vertex, then there'd have to be 1, 2, 3, 4 more vertices, but I've only got 4 to start with, and so I won't have a tree with 5 vertices in this way because it's got 1 more than I need. And so I can't have anything with degree 4 or more. I've got the one of degree 3, I've got the one with maximum degree 2, and so we've got all our trees. So there's all our unlabeled trees with 4 vertices. There are two such trees. So let's have a look at the next example. Now we're going to draw all unlabeled trees with 5 vertices. So pause the video, try it out yourself. Okay, let's see what we can do. We want to draw all trees with 5 vertices. We can say, well, let's start with the ones that have maximum degree 2. So if I've got maximum degree 2, that means I'll have a vertex degree 2, another vertex degree 2, another vertex degree 2, and then I'm going to have these two ends that have degree 1. So there's one such tree. We'll call that one T1. And maybe I'll write this down as the way I got it was I looked at max degree 2. Okay, let's try a next one. Max degree 3. So I'm going to start with a degree 3 vertex. There it is. And that ate up 3 more vertices. So now I've got 1 more vertex. I've got a 5th vertex I can add into the mix. And so that 5th vertex, I can either add it up here, or I could add it down here, or I could add it over here. But I can't add it here. Why can't I add it there? Because I'm trying to draw one that has max degree 3, and that would have a vertex now of degree 4. That center one would be degree 4. So I can't add it there. So maybe I'll add it on the end here. And that's going to be the same as I would have got by starting with that same structure. This is the same one I get by, adding that edge and that vertex up here. That's the same graph. It's consisting of, if I imagine taking this and just sort of bending it out there, it's that sort of same T-type structure. It looks like the letter T. In this case it would be flipped over, and the other one it's rotated, but it's still got that same T-type structure. So that tells me I've got all of the graphs of, or all the trees on 5 vertices with max degree 3. If there's only one of them, we'll call this T sub 2. How about max degree 4? Well, I've got that vertex in the middle. If it's going to have degree 4, I've got to have 4 edges coming off of it. And there we go. And that's all we can have. So we've drawn all our unlabeled trees on 5 vertices. There are 3. There are 3 such trees. Then we could ask questions such as, how many labeled trees are there? If I was to actually put labels on these vertices, then there will be more trees because, for example, if I was to stick the labels 1, 2, 3, 4, 5 on that tree, but then I was to consider the tree that had labels 1, 2, 3, 5, 4, those would be different as labeled trees. These are different as labeled trees. So now this question of how many labeled trees are there, it's about how we can throw labels on these. And I'll leave that, so it's an exercise here, so I'll leave that for you to ponder. But I will say that we just build off of the results that we have here. So we've got this tree type T1. It's a path. Now I want to throw labels on it. Well, just figure out how many ways you can throw labels on the vertices to make different labeled trees. And then we've got that one T2. How many ways could I throw labels on those vertices? And so we can consider each of those cases and then count within that case. And then the last one, we sort of have that 4-spoke kind of wheel type shape. How many ways could I throw labels on those vertices and get different trees? So I'll leave that for you to ponder. And I've also got another exercise here that I'll leave for you to ponder as well. If G is a tree and it has n vertices, how many edges must it have? Give you a bit of a hint here from our previous examples. If you got n vertices, how many edges are there? Well, We drew some examples with 5 vertices, and you can count up the edges. In all cases there was 4 edges. So with 5 vertices, there's 4 edges. With 4 vertices, our examples had 3 edges. So that might give you an indication as to what the answer should be, but then it's really more of a question about how to prove it. If you have n vertices, you're probably expecting then to have only n minus 1 edges. How can we prove that? That kind of proof is something we are not going to do this early on in the course, but when we get to the graph theory near the end of the course, we will do proofs on these graphs and tree structures. And in this case, we do something like a proof by induction. But that will come later. This is just a bit of foreshadowing to what we still haven't started to discuss about graphs and trees. Right now, we're introducing graphs and trees as just one kind of object that we can start counting things on as well. All right, that's it for this lecture. Thanks for watching, and we'll see you in the next one.